Hello, these are the solutions to activity 13. This is the final activity for Chem 1210 this semester. This activity covers chapters 10 and 11. Okay, so our first question says the Goodyear blimp contains this volume of helium at 24 degrees C and 771 torr. How much helium does the blimp contain in kilograms? So the way we would use the ideal gas law, PV is equal to nRT. So N is PV over RT. And then we can plug in our pressure. We just got to go 760 torr to ATM. Volume, we'll keep it in liters. And divide by our gas constant. And times our temperature in Kelvin, 297. And one other, so 770 divided by 760 times 5.1 times 10 to the 6. Just hit the clear button on my calculator. 770 divided by 760 times 5.1 e to the 6 divided by the gas constant divided by 297 gives me the number of moles. So this gives us moles. So the torr cancels, ATM cancels, liters cancel, Kelvin cancels. The only thing not canceling here is 1 over moles, or 1 over moles. And so that gives us moles. So this is 2.12 times 10 to the 1, 2, 3, 4, 5 moles. And then to go to kilograms, we'll just take this number of moles times the molar mass. So 1 mole of helium is 4.003 grams, and then 1,000 grams is a kilogram. So times 4 divided by 1,000 gives me 850 kilograms. So 8.50 times 10 to the 2. Question 2, the pressure of a gas is inversely proportional to what properties? So P is equal to nRT over V, inversely proportional to volume. So inversely proportional is 1 over volume. So, but temperatures are direct. Pressure and temperature are directly proportional. So only 1. Question 3, sample of an ideal gas has a volume of half a liter, 25 degrees C, and 1.2 atm of pressure. What is its volume at 75 degrees and 3.6 atms? Okay, so 2 ways we can solve this problem. There's maybe even more than 2 ways, but one thought is we can take the moles of this gas from PV over RT, and then we're going to change the temperature and the pressure, and then we can go calculate volume. So one thing we can do here is we can plug in for the initial set of conditions, we can say 1.2 atm times half a liter, divide by our gas constant, times 298 Kelvin. That'll give us a number of moles of this gas in this container. Which is 0.0245 moles of gas. And so then what we're doing is we're changing the temperature, we're changing the pressure, We want to know the new volume. The moles are going to stay the same. So our V is going to be nRT divided by P. So we can plug in our moles, then we can plug in the new temperature, we can plug in the new pressure, and then calculate that volume. So the key is that the moles of gas is staying constant, it's not changing under these set of conditions. And so then we can plug in and solve, take our moles times the gas constant times the new temperature. So that's 348 Kelvin, and then divide by 3.6 ATM. Gives me a volume of 0.195 liters. So this is method one, is calculate moles. Moles doesn't change, so then just change our temperature and pressure, calculate volume. So our option two would be to recognize that what we have here is we're taking our pressure, volume, and temperature, which is equal to RT, and then there's some initial set of conditions for these. This is equal to NR. So nRT equal to PV, just dividing by T, and then recognizing P1 V1 over T1 equals NR. And then NR is also going to equal P2 times V2 divided by T2 if we're keeping the moles of gas constant. And so then we could write P1 V1 over T1 equals P2 V2 over T2. Only caveat is we have to still convert to Kelvin. It may appear that we can leave this in degree C, but we can't. We still have to convert to Kelvin. Okay, and so then we can solve for V2 by going P1 V1 over T1 and then times T2 divided by P2. And so if we take, P1 and V1 is 1.2 ATM times half a liter. Let's actually write this out here. So our V2 will equal 1.2 ATM times half a liter, but times 348 Kelvin. In this chapter, everything's going to Kelvin. We can't leave anything in degree C. And then so our T1, 298 Kelvin, and then our P2, 3.6 ATM. I'm just working this out here. That also equals the same volume, 0.195 liters. So two approaches here for question 3. Question 4, which molecule would effuse from a pinhole the fastest at room temperature? It doesn't matter at any temperature. Meaning, like, if we identify the fastest at room temperature, it's also going to be the fastest at some other temperature. Okay, so the fastest to escape is going to be the one that has the highest velocity, the highest, most probable velocity, or the highest root mean square velocity, just one that has the highest velocity overall, where this is 2 RT divided by molar mass, this is 3 RT divided by molar mass, where the lighter we make the gas, the greater we make that velocity. So we want the lighter particle, and so our masses here, just the atomic weight of these guys would be 16 AMU, 18 AMU, 32 AMU, and 4 AMU. So our lighter particle here is helium. It travels faster in this gas mixture. It's going to be the fastest to escape. Question 5 is asking about the Van der Waals equation. So the Van der Waals equation looks like this. P plus n squared A divided by V squared. Not minus. And then times V minus NB is equal to nRT. And so B is all about the size of molecules. So this is the molecular size of the gas particles. Then the A is directly proportional to the strengths of intermolecular forces of attraction. And so, which is the definition of the B constant? So real gases consist of atoms which occupy a finite volume of their container. That is the statement of what the B is corresponding to. The average speed of molecules in a real gas sample increases with temperature. This is from the kinetic molecular theory of gases. True statement, but has nothing to do with the B constant. And so that's just one of the postulates that the average speed is related to temperature. There are attractive forces between the atoms or molecules of a real gas. This is the A constant. That's what the A means in the van der Waals equation. And then the rate of diffusion of a gas is inversely proportional to the square root of the molar mass of the gas. This is just the relationship between velocity and molar mass from an equation like the RMS. Velocity is 3 RT over molar mass, the square root of this. So you get this inverse relationship to the molar mass. So true statement, but nothing to do with the B constant. So the right answer here would be statement A. Number 6, we have a gas mixture here. So we have like a valve where we're going to mix two gases. And so the two gases are going to mix together until they equilibrate. And so we have 3 liters of 2 atm of oxygen and then 1 atm of nitrogen. You can imagine that high pressure is going to go to the low pressure until the equalizing pressures. And this isn't drawn to scale. So 3 liters is a little bit bigger in volume than the 2 liters of 1 atm of nitrogen. And so the question says, what is the partial pressure of oxygen once complete? And I'll also calculate the total pressure. And in fact, the total pressure is like, you might think it's 3 atm, but that doesn't make any sense, right? That it's not going to be 3. You may think it's the average, it's not the average. So we might want to calculate the total pressure here too. And so the question is asking for the partial pressure of O2. What's going on for O2 is it's going from having a volume of 3 liters to now a volume of 5 liters once we open up this valve and mix these two gases together. And so we just have a P1 times B1 of O2 initially, and then our PO2, our VO2 final set of conditions. We're just going from having 3 liters to 5 liters. And so we have our PO2 final will be equal to our initial pressure, 2 atm, times 3 liters, divided by our final volume of 5 liters. So we have a P1 V1 equals P2 V2 problem that we're solving here. And so our partial pressure of oxygen is going to be dropping due to the expansion into a larger volume. So 2 times 3 divided by 5 is 1.2 atm. So the partial pressure of oxygen, 1.2 atm. Now the question could have said, well, what about nitrogen's pressure? So the partial pressure of N2 final would be equal to the 2 liters of nitrogen times the initial pressure. So the P1 V1, 1 atm. It's also expanding to the 5 liter volume. And so this would be 0.40 atm of N2. So 1.2 atmospheres oxygen, 0.4 atm N2. And so our total pressure will be the partial pressure of nitrogen plus the partial pressure of oxygen once they mix. So that would be 1.6 atm from 1.2 plus 1.4, or 1.2 plus 0.4. So 0.4 for N2, 1.2 for O2, 1.6 for the total. Question 7. We have a sample of air warmed to 114 degrees C. What is the new volume? So we have this volume at 23 degrees C warmed to 114. What is the new volume if the pressure remains constant? And obviously the moles is remaining constant too. So if we have PV is equal to nRT, but then the pressure remains constant, so let's divide pressure over to here, and then the temperature is changing, so let's divide by temperature over here, and so then we divide it by pressure and temperature, so we have this. And so these are constant here. So V over T equals a constant set of conditions. And so our V1 over T1, we change volume and temperature, keep everything else constant, that same constant is going to be equal to V2 over T2. So hence V1 over T1 equals V2 over T2. And so then what is the new volume? So our V2 is going to equal to V1 T2 divided by T1. Now again, like it seems like you might be able to leave this in degree C, but we have to convert to Kelvin. So the reason why is 114 over 23 doesn't equal, if I convert 114 plus 273, that's 387 Kelvin. And 23 plus 273 is 296. So the ratios aren't the same. 114 divided by 23 is 4.96. That's not 387 divided by 286. So you have to convert to Kelvin in these problems. You get a different ratio if you leave it in degree C. Okay, so our V2 is going to equal V1, 2 liters. Let's think for a minute too. We're warming, so we got to expand the volume. So the V2 should be higher than V1 is our prediction here. And so even if we take a look at our answers real quick, we can rule out A and D. That can help us if we make a mistake in our temperatures here. If we get these backwards, maybe we'll catch our mistake. So V1 times T2 divided by T1. So 2 times 387 divided by 296. Temperature, or the volume went down. Wait a minute, what did I do? Oh, I typed it in wrong. It's like I did that on purpose. I did 2 times 287. So it's 2 times 387 divided by 296. So I did catch my mistake for the exact reason I was saying we should be able to catch it. I got a volume that was 1.95, which can't be 1.95. It starts at 2, has to become bigger. I do the arithmetic correctly. It's 2.61. Okay. So maybe a good example on why it's good to think about the range of what the answer should be ahead of time, so that if you do make a silly mistake, I almost made a dumb mistake of just putting the wrong number in the calculator, and I easily caught it. Of course, 1.95 is not a choice, so in a multiple choice test, we would catch that mistake that way too, probably. Okay, question 8. It deals with the kinetic molecular theory of gases. This deals with the postulates like gases are moving randomly in a container, random motion, that the gases occupy a negligible portion of the container, so they're not occupying much of the space of the container, and that their temperature is proportional to the kinetic energy of the distribution. The kinetic energy is related to the average velocities of the gas mixtures. So gases in random motion, that's a statement of the kinetic molecular theory of gases. So that's not the answer because we're looking for the wrong answer. The sizes of the gas particles are negligible compared to the size of the container. That is a true statement of the molecular theory of gases. The gas particles do not attract or repel each other. That's also a statement of the kinetic molecular theory of gases. And then when gas particles collide, kinetic energy must be conserved, not lost. So statement D is incorrect. So when two particles collide, what this means is you have fast particle. So we have, particle A traveling fast hits particle B, which is traveling slow. Then maybe particle B deflects off faster, and then particle A slows down. So maybe A goes slower, and B goes faster. But the kinetic energy has to be conserved. We're not creating or destroying energy through collisions. Question 9. In a mixture of N2 and O2, the mole fraction of N2 is found to be 0.7. In terms of symbolics, like X is our mole fraction. Fraction of the moles in the mixture, that's the one component. So the N mole fraction of O2, 0.700 to unitless quantity. The total pressure of the mixture is 1.4 atm. What is the partial pressure of oxygen? Well, we know that the partial pressure of a component is equal to the mole fraction of the component times the total pressure. this is the Dalton's theory, Dalton's law of partial pressures. There it is, Dalton's law of partial pressures. And so the mole fraction of O2, because it's the only other component, has to be the other fraction, so it's 0.300, and then times 1.42 atm gives us the partial pressure of O2. So the partial pressure of O2 should be 0.3 times 1.42, that's 0.426. So that's the partial pressure of O2. Doesn't ask for it, but the partial pressure of N2 would be 0.7 times 1.42, and that's 0.994. And obviously, if you add the two components up, the sum have to go to the total. The total, just checking here, 0.426 plus 0.994, 1.42. So it checks out. Okay. Moving on to number 10, rank the following substances in order of increasing boiling point. Sorry, I'm just looking like something wasn't quite formatted right. There is 1, 2, 3, 4. Okay, I don't know why there's an extra parentheses here. Okay, so we're ranking this molecule, Cl2, krypton, and then this molecule. Okay, so let's look at the first one here. So I have carbon with 3 CH3s off of it. To a CH2 to a CH3. So I'm comparing this with this one here. This is octane. I'll just take a moment to write all the carbons out. 1, 2, 3, 4, 5, 6, 7, 8. I just want to take the moment to count my carbons 1, 2, 3, 4, 5, 6. One, two, three, four, five, six. How did I miss? Okay, I mean this would have made more sense if they were the same formulas, and maybe I'll fix this because ideally these would be the same. But it still is actually like we can still get the right answer. As it's, okay, rambling here, but the straight chain is better, and having more carbons is better too. So, and if I'm comparing, calling this one A and this one B, B is better in terms of intermolecular forces than A because it's a straighter chain. Straighter chain's better because they can interact and push their electrons around more easily, induce that dipole moment, have greater dispersion forces than the branch structure. And then it's also bigger, it has 2 more carbons. So we have a C8H18 for the last molecule here, and the CH3C, this molecule here, is again 1, 2, 3, 4, 5, 6. This is a C6, and it's going to be H14. So 12, 14, or excuse me, 9, 10, 11, 12, 13, 14. So we have a hexane versus an octane. And so B, bigger and straighter chain is better than shorter and branched. And then in terms of krypton versus Cl2, so krypton is going to be the lowest just because it's one atom, and its molar mass is about 83 AMU. Cl2 then comes next, it's about 71 AMU, similar in size, but having the 2 atoms is better. And then the C8H18, way more atoms and also bigger. So like and then same thing with the C6. So the molar mass of the C6H14 is 6 times 72, or excuse me, 6 times 12 plus 14, so that's about 86 AMU. So I think I intended this to be CH3, CH2, 4, CH3. So they're both hexane isomers, but still the straighter chain is going to be better. So that we go molecule A, then molecule B. And so that's going to look like choice B. Is our ranking of boiling points due to our ranking of intermolecular forces. So ranking in order of intermolecular forces is the same as the ranking by boiling point. Number 11, in its liquid state, which intermolecular force does ClF5 contain? And it's a square pyramidal molecule. And so the idea here is, from a Lewis structure, 7 times 6, 42 electrons, we end up in the octahedral geometry. We'll put fluorines in 5 of the places, so that's our 5 fluorines, lone pair around each. I'll just do one of them. That's 8 times 5, that's 40 electrons. 2 leftover electrons. Let's put those here. And so this is that square pyramid. And so this molecule here is definitely polar. So by being a polar molecule, this molecule contains dispersion forces, because all molecules have dispersion forces, and dipole-dipole forces. But no H bonds. We need F directly attached to a hydrogen atom. No H atoms at all in this molecule, so we cannot have hydrogen bonding forces of attraction. And then there's no ions present, so we need to have ion dipole forces. We need like an ionic compound dissolved in the solvent. So definitely no ion dipole forces, but we definitely have A and B. And no H bonds. So if you see hydrogen bonding, that's the force of attraction. Hydrogen bonding force of attraction is H directly attached to NO or F. The substances below have molar masses that are within about 2 grams per mole of each other. Which one has the lowest boiling point? And so here's our nonpolar molecule, and these others are polar. And so our lowest boiling point is going to be A, because it's the one that's nonpolar here and only has a dispersion force being similar in size. I think we could predict the highest. The highest be the one that H bonds. So only one of these has hydrogen bonding force of attraction. That's ethanol. So I think ethanol would be the highest here. And then these two, we might remember that dimethyl ether was lower than the acetaldehyde from the example in class, but I don't think we could predict that. So I think that's just, if we know there are dipole moments, we might be able to predict that. But the ethanol is going to be higher because it has H bonding, and the other ones don't. So just remember, the presence of hydrogen doesn't mean the substances has quote-unquote hydrogen bonding. So a hydrogen bonding intermolecular force of attraction is when H is attached directly to NO or F. And H is only attached directly to O in ethanol in these cases here. In this one here, we have C double bond O to H. And so the H is directly attached to a C. So no H bonding for D. So I think we can predict the highest and lowest for 12. 13, which molecule in a liquid sample, or the molecules in a liquid sample of pure dichloromethane experience which of the following intermolecular forces of attraction? We have to be a little careful on this one. And this one, I think, tripped a few people up on midterm 3 on one of the questions. That something like dichloromethane, you might look and say these are opposite, so this molecule here is nonpolar. You might predict that. And the answer is no, it's not nonpolar. We have to go to its actual molecular geometry, which is tetrahedral, and look at the structure here and see, this bond's actually bent. It's 109.5 degree angles. We got a partial negative charge on this side of the molecule that's not matched on this side of the molecule. Different charge over here. So we are going to have some built-in charges on dichloromethane. So this molecule is indeed polar. So by being polar but without H bonding means it has dispersion forces, dipole-dipole forces, but no H bonding. Has hydrogen bonds between C and H, but not the hydrogen bonding intermolecular force of attraction. So only 1 and 2. Then our final question here in the activity, which of the following molecules can form intermolecular hydrogen bonds as a pure liquid? So this is the force of attraction. So we need the F attached directly to H. This F is attached to a carbon, so 2 doesn't do it. 1 is ethanol. We talked about that earlier, so that definitely forms hydrogen bonds. 3 does as well because we have nitrogen with hydrogens attached to it. And so that's going to create polarized nitrogen, relatively small, partial negative, partial positives on the small hydrogen. So we get that strong energy between our molecules for our H bonding between molecules of 3, but then not for 4. So we need the H directly attached to NO or F because they're the smallest atoms of the greatest electronegativity. Sulfur is just too big. Okay, so 1 and 3 can do this, and that's it. All right, so that's it for the final activity.